Hey everybody, video number 4. We are going to learn about the oxidation and reduction half reactions and how do we balance chemical equations, conservation of charge. So how do oxidation numbers change during a single replacement reaction is what we're going to be working on today. Identifying and writing oxidation half reactions. If you can't see that half in there, is that what it says? Half reactions to show the movement of electrons. And last and not least, identifying oxidizing or reducing agents. So this particular video is rather importante. So step 1, finding the metals that are moving. Okay, here is a balanced chemical equation, and Mg and Ca are the two metals that are swapping. So the lone metal on either side is obviously what's swapping out. And notice the Br2 is just hanging out. Okay, we need to track the oxidation or track the changes in oxidations for all elements. So Mg goes from +2 to 0. And if I were to leave those up, you would see that in the compound, it's going to have a charge. When it's a lone element, it's going to have a 0. So that's what I'm going to ask you to assign first, is all the zeros first. Okay. And the Ca is going to then go from a 0 to a -2. Or I'm sorry, a +2. So there was two electrons moving. Okay. Note the spectator ion experiences no change in oxidation numbers, and in this case, it is going to be generally the negative compound or the negative ion within the compound. Generally, if it's a polyatomic, that really helps those things never change their oxidation numbers. And then to write out the half reactions is to take this Mg +2 going to Mg0, and then just figuring out which side the electrons go. And it makes sense that it goes on one side and not the other. Okay, so this is what we need to figure out. I have Mg +2 going to Mg0, and I just need to figure out which side are those electrons going on. So they could be on either side. We just need to figure out which one makes sense. So if I were to cover up this set of electrons on the product side and say Mg +2 plus 2 electrons equals Mg0, does that make sense? And that's actually the one that does make sense, right? If I have a +2 charge, I have 2 more protons. Protons are winning. And so I need those 2 electrons to get back to even. So that one makes sense. This is now gaining electrons, and I got oxidation is losing this one. So this is the reduction. Oh, and notice my charge is reducing. It's going from +2 to 0. See how that works out? Then same deal with CaO and Caa +2. I know there's 2 electrons in play, but which side are those electrons really supposed to be on to make this whole thing work? And it turns out it should be on the product side, because I have Ca with a 0 charge going to Ca with a +2. And how did I do that? I lost 2 electrons. So those these two sides are equivalent. Ca +2 plus 2 electrons is the same as CaO. Okay. Then when I put those two things together, everything on the reactant side stays on the reactant side. Everything on the product side stays on the product side. Cancel out the electrons, and I'm rebuilding my equation. Okay. Overall half reactions show both half reactions the equal number of electrons on both sides, so they cancel out. When we get to it, if they don't have equal numbers of electrons, I must balance them. And you'll see, I'll show you how that works. It'll be the last of my examples. Okay. Reduction half reactions must show the element that is being reduced. Okay. Both forms of the metal are shown, reactant and product, with the numbers of electrons gained on the reactant side. Reduction has electrons on the reactant side. Maybe that helps remember it that way. Oxidation is equal and opposite. So of course, just the elements that are being oxidized. Both forms of the metal are shown. Product side has electrons. On oxidation, it's losing. Just like when exothermic is losing, that heat is on the product side. Here, the electrons will be on the product side because they are losing. I think we just need to get into some actual examples of how we go from one to the other. Oh, first let's define these guys one more time, because these guys are a pain in the butt. Oxidizing agents. This is the element that is being reduced because it's responsible for the oxidation. So if I'm responsible for the oxidation, I am actually being reduced because I'm the one that gains the electrons. Okay, I am being reduced. My role, we call them oxidizing agent. Okay, opposite is true for reducing agent. It is the exact opposite. Again, it's the actually element that's being oxidized. It is responsible for the reduction. And I'm sure you just took a second, wrote that all down, and I'm now going to move on and show you how we do this. So the piece I don't have on here, I do have the oxidizing and reducing agent. Good, so we're good. So I'm going to ask you the first time through is to just assign the zeros. So find your lone elements and put zeros there. Okay, that's good. And then I look up and I see zinc has nothing but a +2 charge, so that works out. But I'm going to go with Cl as a -1 because I see Cl only has a -1 charge as its negative choice, which is I have to take because remember the second element is always negative. I have two -1s, therefore Zn must be a +2. And in MgCl, I have two -1s, so Mg must be a +2. So assigning those oxidation numbers is key. What you'll see when I'm doing these is I'll take that Cl -1 and I'll put a line through it now, generally, because this is what we call the spectator ion. And I didn't have a space down here for spectator ion. You will have a space for this in the practice. So the spectator ion, I will ask you to identify, and in this case, it's Cl. That's just to help you when we get to the practice, okay? And I generally just do that, so now I can focus on what's what. I've started these oxidation half reactions for you. I might not do that in the practice. I'll expect you to pick it up just from the 0 to the +2. I see that MgO is going from Mg0 to Mg +2. Now that I've put that +2 up there, I can just bring it right down. It is on the product side. And then to do this, I get a +2 electrons. So there's my oxidation losing electrons. And then my reducing agent is the thing that is actually being oxidized. It's responsible for the reduction. So that is the Mg0. Good? Okay. The opposite now, the reduction. So where is my charge going down? Now, a lot of times when I'm at the board doing these, I'm actually going to ask you to do this one first so that the other one pops out a little bit and makes it easier. Which one has my charge going down? And that's +2 to Zn0. So I'm going to put the Zn0 in, and then what did I need to use? How many electrons did I have to gain to get from 2 to 0? I must have gained 2 electrons. Notice my electrons now equal, so I'm set. I don't have to balance this. And here's my oxidizing agent. It is the Zn +2. Notice the pattern here. It is the thing on the reactant side. You can't put products as agents because they have already been reduced or been oxidized. So it's the species on the reactant side. Maybe a little side note, okay? We got 2 more examples to get through, so let's get into example 2. Again, same process. I'm going to find the lone metals and put zeros on my lone metals. Those are my charges. And then I tend to take that plus and then do the minus first. In this case, Ag has one choice, so I could have done Ag first. Hg, mercury, has 2 choices, +1 and +2. So I can't do that first. I have to do the minus piece first for that particular compound, okay? So I tend to have it to do the negative first because that has less options. And then if I have a -1 on AgCl, the Ag obviously must be +1 to cancel it out. And if I have a -1 on the HgCl, then the Hg obviously must be +1. Go ahead and cross those Cl's out. Those are my spectator ions. They're just watching like a spectator, okay? Tracking my Hg now. Hg goes from Hg0 to Hg +1. How many electrons? 1. Reducing agent, Hg0. Okay, he's the guy that is responsible for the reduction. He's the guy being oxidized. Okay, Ag +1 is going to go to Ag0. On the product side, it's Ag0. How many electrons did I gain? Boom, +1. Oxidizing agent then is that Ag +1. Starting to get a feel for this? Okay, good, because we're going to do it a bunch of times. Next one, this one is slightly more complicated. This is where things get fun. I'll show you, as we put in the oxidation numbers, why it's more challenging. Again, first thing, lone elements get a 0, so 0 and 0. And then NO3 is a polyatomic ion that is a -1, straight up. And if there is only one NO3 in AgNO3. Notice I didn't put parentheses around it and then put a 1. If I put parentheses around it, you'd see that there's just one of them. So the Ag is a +1. On the other side, though, with the copper nitrate, there are two NO3s. That's a total charge of -2. Therefore, copper must be a +2, and copper has a +1 and a +2 choice. So I had to use the negative to figure out the positive. And do you see the difference here? The positive numbers are not equal like they were in the first two. That means we will have some extra steps. But we will go through and finish the rest of it the way we normally would. I see Cu0 on one side, I see Zu +2 on the other side. Therefore, I must have lost 2 electrons. Reducing agent, obviously Cu0. Notice I've set these up so that the reducing agent is the actual thing that we're talking about to help you figure out what they are and be able to successfully do it. I have Ag +1 on the reactant side. It goes to Ag0 on the product side. So notice I put it on the product side. And then how many electrons did I gain to get from +1 to 0? Well, I gained 1 electron. And here's where we have a problem. 2 electrons on one, 1 electron on the other. We need to fix that. Okay? So first off, the oxidizing agent, we can go ahead and put that in as Ag +1. It's got to be on the reactant side. But I need to double those electrons. So what I need to do is take this, because these are not equal, right? That is a big key here. Now we've got to deal with conservation of charge, which is what it's called, and it's just another way to approach balancing balancing equations. I'm going to multiply this whole thing by 2. When I do that, I can distribute the 2 just like we learned in math, so that becomes Ag2. I'm going to get 2 electrons this way, and then I'm going to get 2 Ags this way, and now that 2 on the outside is gone. I've distributed it through. And then all you need to do now is, because I put a 2 in front of the Ag1, I need a 2 in front of the Ag1. And I put a 2 in front of the Ag0. I need a 2 in front of the Ag0, and now we are finished. And notice we needed to do that anyways from the normal balanced chemical equation. I see that there's 2 nitrates on one side, 1 nitrate on the other. I would have put a 2 in front. That 2 would have affected the Ag, and this would have ended up following the way we would have normally balanced an equation. This time we just saw that we needed to balance the equation based on the equal numbers of needing the equal numbers of electrons. With that, you've seen some examples. We've walked our step through it. I would do it very much the same way every time. Always start with the 0 and then use the uncrisscross method that we used from last notes to finish this notes and start writing half reactions, oxidation and reduction. And with that, we're done. Good luck and happy half reactioning.